Heungno Lee. This is a work done by one of my students while he was working for his MS degree, master's degree at GIST. And then he is advised by me. Okay, and then the name of the talk is Compressed Measurements Needed for Noisy Distributed Compressed Sensing. Okay, and this talk is done today, is also going to be presented about maybe 2 weeks later in ISIT 2012 at MIT. So it's going to be the same talk. All right, so briefly introducing me, I'm directing this lab, InfoNet lab. So basically this lab is doing this type of work: information sensing, processing, controlling network. So I do everything. So basically I'm originally electrical engineer. I got my degree at UCLA, and I'm not a mathematician like you guys are. So my PhD was on wireless communications and the wireless networking and information theory and those things. Those are the stuff that I teach at GIST. And then here is the depiction of the job that lab is doing. So basically today's network, basically we have information collecting unit, sensors, and then there are processing units which does processing, and then there are some decision units, and then if you put them all together, basically that's the brain of your body. So basically future network is going to be like this. That's what I envision. So that's the name of this lab. Okay, so in the future network, just like a human body, network will have a sensing unit like eyes, ears, and hands, and then processing unit, and then controlling unit, hands and legs, and then you exert your forces to the environment. So basically, that's what I'm thinking about. And then this is the picture that I always use in a talk. I like to play soccer, and then every Thursday I play soccer with my students. Okay, so that's that. For agenda today is compressed sensing. What is it? Because this talk is a master's degree type of talk, so it is very narrowly focused. So I'm not going to talk about what I do in my lab. So I'll just talk about one topic, narrowly focused topic. So that involves the compressed sensing. So I'll briefly introduce you what compressive sensing is. Maybe you guys already know, but I'll repeat it. And then multiple sensor system. That is the application area that I use compressive sensing. And then I'll talk about that a little bit. And then problem statement. And then our approach. And then talk about the result. So here is what I mean by compressive sensing. The compressive sensing that I mean is the sense done by, suggested by Donoho, like 2006. And he says, he gave this statement: why go to so much effort to acquire all the data when most of what we will get will be thrown away? Can we not just directly measure the part that will not end up being thrown away? So that's what he said. Basically, he was referring to transform-based compression. For example, of Fourier transform. When you have a data, you take a Fourier transform or wavelet transform, and then you found out there are only few coefficients that are significant. Rest of them are insignificant, and then you throw them away, and then basically that's the compression. Just collecting the most important parameters. So that's the data reduction. But he says, instead of going through all these steps, can we just, if we already know that the amount of information inside the signal is very small, then can we just take small number of samples directly? That's what he said in one of his transaction paper in Information Theory, 2006. And that's what we call compressed sensing today. And then he later on became more bold, more brave. And then he said that sampling theorem is wrong. And he says this is not literally wrong, but psychologically wrong. Basically, it tells the engineer to take a lot of samples. It gives a psychological pressure, he's saying. But you don't have to take that many samples. That's what he's saying, right? But these type of things have been already noticed in Shannon's. Basically, data reduction can be done from signal. When you find a certain amount of correlation inside the signal, you can compress the data. For example, let's say human ear can process amplitude information very well, but not the phase information. So you can ignore all the phases in sinusoidal signals. So basically, he said that data reduction can be done, Shannon. So he's basically saying these things, Donoho. And then compressed sensing tutorials these days, you can find in the internet. Many of them is basically witnessing what Donoho said in the 2006 paper. Basically, here is the only original image. You take wavelet transform, and then you notice that there are only certain small number of coefficients that are significant, rest of them very small, so you can throw them away. And then after you throw them away, and then you reproduce the picture, then the original picture and then the approximated picture with the very few percentage of the original samples retained is very similar with each other. So basically compression can be done. Okay, so that's you can find many tutorials these days in the internet, basically verifying what Dono has claimed. Okay, all right. These are the charts from Romberg and Watkins and so on. So you can Google it, right? And then compressed sensing, because of this paper that he published in 2006, and then his colleagues, his students, and then his colleagues basically made this very popular. Okay, and then one of the MIT technical review says top emerging technologies include the compressed sensing, especially compressed sensing camera like this. And then it has a lot of citations today. So basically, what is the CS that he formulated? Basically, that CS problem can be written this way. So it is a y is equal to ax problem or fx problem in this notation. So there is a vector, and then there is a matrix, and then there is a signal. And then what Dono says is, if x is a sparse signal, that means number of non-zero elements in x is very small compared to the ambient dimension of the signal. Then you don't need a lot of measurement. Then you don't need all the measurement, but you need a small number of measurement. How small? That depends on the sparseness of the signal. So basically, and then that's the story. And then he also suggested making use of L1 norm minimization instead of L2 norm minimization. Let's say if we want to find a sparse solution with a small number of measurements, you have an underdetermined problem, and then in this type of problem, if we use the L1 norm criterion, you can find the sparse solution very well. So basically, this is the case. And then there are lots of engineering applications that this type of equation and then solution can be applied, including cameras, medical scanners, and so on. Basically, those are the stories. So basically, number of measurements is going to be smaller than the ambient dimension of the signal. With the M measurements, you can reproduce signal X. That's the problem. Okay. And then, so I basically summarized the compressed sensing narrative in maybe a couple of statements. So they are this. So this is a single chart summary of compressive sensing theory. So basically, they say any natural signal X can be sparsely represented in a certain basis. So X is equal to BS, where S is a sparse signal. So X is any natural signal, like an image or a speech waveform. And then you can find the kernel B. This kernel is a square matrix. And then if you have a signal like this, you can have a small number of measurements, which is good enough to recover the exact signal X. So that's what they are saying. And then this A matrix is called a sensing matrix. And then there are different kinds of matrices they suggested. One of them is Fourier transform matrix. The other one is Gaussian sample matrix. And then the other one is Bernoulli, and so on. And then L1 minimization recovers this signal X perfectly with the probability very close to 1, as long as the number of measurements is good enough, large enough. So basically the problem is ambient dimension is n, and the number of measurements that you need is smaller than that n, m, and then this number of measurements should be certain multiple of sparsity, the number of non-zero elements in the vector X. So that's the main line of compressed sensing theory. So here, that's a quick summary of compressed sensing theory. And then we are trying to apply that theory to a multiple sensor system. So I'll talk about what multiple sensor system is. So in a multiple sensor system, sensors are distributed in a limited region. So as you can see here, so there is a geographic area, and these are the sensors deployed, and then they make measurements. And let's suppose that the measurement each sensor is making is a sample of a large phenomena. Let's say in this particular example, I use a temperature case. So high temperature, lower and lower temperatures. These are the lines, equi-temperature line. And then basically then in such a case, then the measurements that one sensor is making is going to be highly correlated with other measurements that the other sensor is making, which is nearby, right? So in such a case, you can easily imagine, how many number of sensors should I use? If you use lots of sensors, then the fidelity of the information that you can gather from the field will be high. But when you do that, there will be lots of data, right? Because the amount of data that you are going to collect is going to be proportional to the number of sensors. Then there is a transportation problem. How do you move these acquired data to a information collection center? So here I call it fusion center. And then the job of the fusion center is try to reproduce each and every sensed signal at the fusion center. So in such a case, basically there is a trade-off. If you increase the number of sensors, then you have to ask the sensors to send the signal to the fusion center. But here we envision that these sensors are cheap sensors so that you can easily deploy in the field. In such a case, sensor is incapable of processing large amount of data. And then sensors also has a small amount of memory. So you cannot store a lot of data either. So in such a case, you have a problem, right? If you use a conventional method, that sensors gather the data and then take the transformation and then do the compression and so on and so on, that requires a lot of power burned at the sensor. But we envision that these sensors are incapable. cheap sensors. In such a case, how can you design a system? That's the problem. Okay, so basically, sensors are distributed in a limited region. Each sensor senses a signal from a common source, let's say, and then each sensor transmits acquired signal to the fusion center. Okay, and then signal feature. By the way, this sign here means this is one of the book chapter that we published this year on this work. All right, and then signal features in MSS. So basically, signals measured by sensors have two types of correlation. One type is intrasensor correlation. The intrasensor correlation exists within the particular signal itself. For example, let's say, temperature variation over time must have a correlation, right? If you have a correlation using the compressed sensing theory, it can be sparsely represented in a certain basis. So basically, that's intrasensor correlation. And the intersensor correlation, like I said, each sensor is making measurement, but neighboring sensors make a similar measurement. So there will be intersensor correlation. So intersensor correlation exists between signals measured by different sensors. And then if we make use of these correlations, then basically we can improve the system performance, or we can reduce the amount of traffic that need to be transported to the fusion center. So the job of the sensors will be much easier. Okay. So basically, structures of two correlations can be modeled this way using compressed sensing approach. One is intersensor correlation. Like I said, it exists inside the signal itself, and then basically we can model it as a sparse signal. So sparse in a certain domain. So basically, sparse signal. Let's say you have ambient dimension of 250, and then there are only a few locations where you have a non-zero element. Rest of them over zero. So this is a sparse signal. So we model our signal this way. And then intersensor correlation. Basically, again, making use of this correlation structure, to model the correlation between two sensed signals, we use the same support set. Let's say support set of, by the way, the support set here means the non-zero indices of these, indices of non-zero coefficients of the vector. Okay, and then here, for example, blue is a sensor one's signal, and then support is maybe here 1, maybe here is 25, and so on. So a collection of those indices where you have a non-zero element. And then in this picture, we are saying that sensor 1 and sensor 2 are highly correlated. Their support set is the same. Okay? But even though their support set is the same, their signal value are different. So signal values are different. So their measurements are correlated, but since their signal values on the non-zero positions are different, so they are not exactly the same signal. So each signal has additional information. They are not correct the same signal. Okay. All right. So that type of modeling that we are going to do. So here we in this picture we would like to depict conventional approach, the previous approach. So basically, intra and intersensor correlation exist. In such a case, what would be the solution in conventional way? Not using the method that we are trying to propose today. Okay. So one approach is this. Basically, each sensor just make a measurement and transmit. And then each sensor independently compresses the data. In such a case, each sensor does not have an information about what other sensor is making as a measurement. So it cannot exploit the correlation exists between data, the sensed data. So there will be limitation in terms of compression. And then now, in order to remedy this problem, maybe you can think about the problem of collaborating. So why don't you share these information with each other? In such a case, you have to allocate channel between the sensors as well. So you need to allocate communications channel, which is a resource. And then allocating communications channels to radios is a highly expensive solution because spectrum is dear. So bandwidth is most expensive one. So that solution is not very good. Even though if they exchange information, they can compress further, and then they can save on the transmission to the fusion center. So this approach is not good. So here is the problem statements. So there are many sensors in the distributed in a limited region, so their measurement must be correlated. Signal samples gathered by FC grows fast. That means the amount of power that should be burned at the sensors is going to be very large. Waste of power. So and then this problem aggravate as you increase the number of sensors. Okay, and then because redundancy in the gathered, that is because there are a lot of redundancy in the gathered signal. And then in order to reduce the traffic volume from sensors to the fusion center, each sensor should compress. But as I mentioned a moment ago, conventional way create another problem, right? Problem of allocating additional bandwidth to sensors and so on. And then additional power need to be burned at the sensors in order to compress. So our study goal is this. Can we make use of compressed sensing approach, aiming to exploit not only the intra-sensor signal correlation, but also inter-sensor correlation? That's the problem. And then we would like to make use of a joint signal recovery routine at the fusion center. So joint recovery routine is making use of this signal correlation that exists between the signals, sensed signals, and then the job, and basically the joint receiver does a good job, and then that reduces the burden of doing heavy compression at the sensor unit. So that's the approach that we are taking. So here is the problem statement, research question. We aim to study the limits of distributed compressed sensing. There is one paper that prior to our work done by Baraniuk's group, University of Texas, Austin, and then they have named this problem as distributed compressed sensing, which is to use compressed sensing at each sensor and joint signal recovery at the fusion center. So in this distributed compressed sensing problem, basically each sensor samples the signal in the compressed sensing way and then simply transmit to the fusion center. The fusion center gathers these data and then do joint recovery of the signal. That's what distributed compressed sensing is. Distributed compressed sensing is of high interest because each sensor works independently with each other, and then basically achieves the high compression benefit. So basically, without talking with each other, you can compress the data. So that's the good part. So in this work, our goal here today is to providing answers to the following questions. How does each sensor compress its signal? That's one thing. And then what is the minimum number of compressed samples at each sensor for good recovery of signal at FC, the fusion center? And then for a given number of compressed samples, how many sensors are required in order to recover the signals. So we would like to see some interplay between number of measurement and the number of sensors. So we would like to study the interplay between these two parameters, number of measurement and the number of sensors. So obviously, if you have a large number of sensors, you need less number of measurement. Okay. So here, how does the required number of sensors change with the noise level increased? So basically, we would like to see the interplay between the noise level in your measurement versus the number of sensors that you need. Okay, so that's that. And here is the scheme that we propose. Basically, each sensor just compressed sample the data and then just transmit. And then at the fusion center, we learn the L1 minimization algorithm. That's the case. So here, here's the proposed approach. Number one, how does each sensor compress its a signal? We said we will use compressed sensing, and basically each sensor compressed samples the signal and then transmit without talking with each other. And then at the fusion center, we make a joint recovery of the signal. And then the question is, basically that's one. And then second one is how to model the inter and intra-sensor correlation in MSS. I'm repeating myself a little bit. So intra-sensor correlation is going to be modeled as sparse signal, and the inter-sensor correlation, basically we will model it as a signal set that has the same support set. So each signal has the same support set. So here a little more detailed modeling is done here. So basically source, we use the notation X. So X1 is the sensor 1's measurement signal, X1. And then we would like to compressed sample it, and then we call it Y1. And then A1 is the compressed sensing matrix for that, used in sensor number 1. And then sensor number 2 does the same thing, a similar thing, right? So Y2 is equal to A2 X2. So these A matrices, they are n by n matrix, where m is smaller than n. And then X are the unknown signals. Then if I have S number of sensors, basically I have S number of equations. And then these compressed signal samples are going to be transmitted to the fusion center one by one, right? Uninterfered with each other. So Y1 received, but in electronics there is always noise. So we add observation noise, N1. We use Gaussian model. So R1 is Y1 plus N1. And then so on and so on. S number of equations. So at the fusion center, we have S number of equations. And then the job of the fusion center is, upon receiving R1 to Rs, try to reproduce X1, X2 all the way up to Xs. So that is the problem, mathematical problem. Okay. So we collect this measurement at the fusion center into a vector. So R is R1 transpose and so on and so on. So you collect them all by concatenating each one of these measurements into a single vector. So the job of fusion center is again, upon receiving R, try to estimate what X is, all of them, okay? So here another illustration showing how we model the inter-sensor correlation. Basically, in each of Y is equal to AX problem can be depicted in this picture like that. The ambient dimension is large. There is a sensing matrix, and then there is a measurement samples. And then the number of measurement samples is much smaller than the ambient dimension of the signal. And then this number of measurements should be a little bit larger than the sparsity, K. K here in this picture is 2. So there are only 2 elements that are non-zero. Rest of them are 0. And then that's intrasensor correlation modeling. And then how do we do the intersensor correlation modeling? I said that we will use the same support set. Basically, here one measurement is done by, let's say y1 is A times x1. Another measurement, let's say y2 is A times x2. So that's the problem. And then here is a little bit of, I have done a little bit of a sloppy job, basically. Here we assume that the measurement matrix for each sensor is the same, are the same. But in our case, we assume that they are different. Each sensor have a different measurement matrix. Okay, so but the objective of this chart is to show how the intersensor and the intrasensor correlations are modeled. Okay. All right. So moving on, and then there are related works as I told you. So Baranyuk's work basically says that number of measurements converges to the sparsity K as you increase the number of sensors. And then they talk about a practical algorithm. So there are practical algorithms that you can use. Oh, I only have 5 minutes? 10 minutes. Maybe I should move on very fast. Okay. So in this case, there are noiseless case, but their measurement matrices are different. And then there are information theoretical work, and their measurement matrix is exactly the same. And then another noiseless work, and then they have shown similar performance. And finally, number of measurements converges to K. And then there is another information theoretic work, but this is not for multiple measurement system, but single measurement system. And the number of measurement is order of K log n, which is famous. And then we are going to use JT decoder, which is Shannon's tool to prove his channel coding theorem. Okay, and then what is JT decoder? JT decoder is a fictitious decoder. It's making use of law of large numbers. So basically, in our case, in our problem, JT decoder is this. So basically, we define a delta jointly typical event. So this event is, let's say, this measurement-related projection matrix, which is defined by identity matrix minus this operator. So on working on each each measurement vector. So basically, the second norm square of this measurement vector normalized this way, and then take the summation this way, is converging to this number. Basically, that's what this one is. So basically, that's definition of delta jointly typical event, and then the decoder makes a decision this way. If you the jointly typical decoder decides a set J is the candidate set, support set. This candidate support set is going to be the decoded set if that is jointly typical with received signal. And then no other set is jointly typical with the received signal. If you have other events other than this, then the decoder declares failure. Then basically there are the error events are 3 kinds. One kind is there is a rank deficiency on the projection matrix, or the other case is the decision is wrong. So a set J which is not equal to the support set of the signal, if it is jointly typical with the received signal, then it leads to the decision error. Or correct set is not jointly typical with the received signal, then it also leads to the decision error. So we consider all these type of decision errors. So basically, the probability of joint typical receiver failure can be analyzed by considering this error event. So error event is union of these things. So basically, this one says R is jointly typical with J, which is wrong, and then R is not jointly typical with correct support set. That's also wrong. And then the event of rank deficiency. And then basically we try to calculate the probability of error in this sense. And then we make use of the union bound approach. And then basically our results, mathematical results are proving each one of these terms converges to zero, probability of error converges to zero as you increase the number of sensors. So basically that's the main result that we have. So since I don't have much time, so I think I should move on quickly. So I'll tell you the results. So our lemmas, we have two lemmas. Basically these lemmas talk about each one of these terms. So basically the first one is the probability of received signal is not jointly typical with the correct set. We have obtained this result as a function of S and the measurement, the number of sensors and the measurement and so on, and then noise variance and so on. And then another one is wrong support set is jointly typical with R. So we have obtained these results. Basically, this one, for example, investigation of this example is quite interesting. So basically here we defined this parameter here, sigma mean square, which is the mean minimum of these numbers, and then each one of these numbers is defined this way. So basically S of I is the ith element of the signal, and then we take the power, and then we define this parameter. And then this one says when we add the signal power, we add only those power that is in the support set, but not in the wrong set. So basically, this one tells you this error probability will be very high when you have a support set which is very close to the wrong support set. So basically, minimum distance neighborhood will determine the probability of error. So long event that are large distance from the correct event will not contribute much, but the close event will contribute toward making errors. So the sketch of a proof is basically, I'm going to talk only about the first one. Basically involves that showing that this random variable is chi-square random variable, basically. Once we model this is a chi-square random variable, we can use large deviation theory to arrive to the result that we got. Okay? All right, so I'll skip these details. And then we use the, so here is what we started with, and then here is union bound, and then we obtained these results from lemmas 1 and 2. And then here we use the union bound one more time, and then this time we find the maximum of this term, and then we call it J star. And then we summarize another result this way. So basically, the proposition 1 and 2 says if the number of measurement is larger than k, then we have shown that this probability linearly converges to 0 with a certain parameter, the rate of convergence between 0 and 1. And then same result for wrong support set. Basically, that the probability that R is jointly typical with a wrong support set linearly converges to 0 with the rate this one defined this way, which is a number between 0 and 1. All right, and then basically the proof is to show that that number is, those numbers are between 0 and 1. Okay, so I'll skip because our chairman says I only have 2 minutes. Okay, all right. So here is the theorem. Theorem is what is the minimum number of samples that each sensor need to make. That number of that number is basically should be greater than k. That's the result that we got. And then once this is satisfied, then the probability of joint typical receiver to fail linearly converges to 0 with a positive rate. That's what it is. Okay, so that's it. That's the main result. And then we have a corollaries, basically, that says how does the number of sensors change as the noise variance increases. Obviously, you need to have more number of sensors. Another corollary is given M, how many sensors do we need for certain performance guarantee? So here we fix the probability of error to be a certain number, and in such a case, how many measurements do you need, and the sensors do you need? And then here is the summary. So I'm happy now I got to the summary part before he says stop, right? So here summary says, we have obtained the 2 lemmas. Basically, they are the upper bounds. We use Chernow bounds to drive these bounds. And then we use proposition. In the proposition, we show the linear convergences. And then we put these results together to arrive at the main theorem. Okay? So from the main theorem, we derive these corollaries. So here is the take-home messages. So sensors with scarce onboard resources, for example, memory unit is very small. The bandwidth allocated to each sensor is small. Amount of power that each sensor can use is very small because they draw on onboard battery. And so in such a case, sensors can make use of compressed sensing to save these precious resources, but still does the job. Compress the signal, send it to the fusion center. Fusion center runs the joint recovery algorithm, and then be able to recover all the signal. So that's the story. And then the number of measurements that each sensor needs to send to the fusion center, as long as it is larger than k, it's okay. Okay? That is a little bit surprising because we know that from the compressed sensing theory that we quickly reviewed, we need log n factor. We get rid of this log n factor. Why? Because we have large amount of data redundancy in the sensed signal. So we can get rid of this. Okay? And then we have used the Shannon's JT decoder. So this has good and bad. One thing is good is because this decoder is a fictitious ideal decoder, the condition that we got is ideal condition. So the ideal result. So this tells us the benchmark performance. And that badness is because this is a fictitious mathematical decoder, you cannot implement it. So you can just use it as a reference. So that's bad part. Okay? And then I want to say one more thing, that basically same type of results can be obtained if you apply to different problems. So for example, think about a camera where you have a CCD camera array. Let's say you have a picture of a person. In such a case, measurements are correlated. And then now you talk about video frames. Then each measurement will be correlated over time. In such case, you have intra-sensor correlation, and as well as inter-sensor correlation. So in such a case, you can apply our result. Okay, and then here are the references. I'll stop. Thank you.